Let us now turn to a consideration of the spread of the distribution around the center. Empirical evidence suggests that as lambda increases, the spread increases, and naturally we'd like to determine what the actual functional form of the dependence on this parameter is. So let's hold lambda as some fixed but arbitrary positive parameter, and we will hide lambda in the notation to keep our expressions more manageable. The natural notion of spread that we will look at is, of course, what we've encountered before in the case of the binomial, the idea of a variance. We think of the variance as a probabilistic moment of inertia. It's going to connote the expected squared dispersion of likely values of your chance variable from the center. How do you define this formally? Mathematically, the variance is always connoted VAR of the chance variable. VAR, of course, stands for variance. It is almost invariably compacted in notation by using the square of the lowercase Greek letter sigma, and we call the variance sigma squared. And it's defined, just as in the case of the binomial, as follows. If the chance variable takes value 0, its distance from the expectation is 0 minus lambda. The square of the distance is 0 minus lambda, the whole squared, and you weight it according to the probability p of 0 of taking the value 0. If the variable takes the value 1, its squared dispersion from the center is 1 minus lambda, the whole squared, weighted according to the probability p of 1 of taking value 1, and so on, and we accumulate all the possibilities. Now, an expression like the one on the right is salutary. It makes very clear exactly what the underlying process is, but undeniably it's a little awkward, a little long, a little clumsy. And we try to summarize this in mathematical notation by using, of course, a summation sign. And we simply say this is the sum over all relevant values k, in this case k is running from 0, 1, 2, 3, and so forth, of terms of the kind k minus lambda, the whole squared, times p of k. Of course, the difficulty in further simplification is in the form of the squared term inside the summation. So let's take a good hard look at this. So now we've got an expression for the variance of a Poisson variable. It's a summation over k of k minus lambda, the whole squared, times p of k. How can we further simplify this? The listener should possibly take a moment, pause the lecture, and see if what we've learned by our manipulations of similar objects in the case of the binomial are suggestive of what we might do here. Restart the lecture when you're ready. Now, in the summation, we've got a whole square, and that is, of course, very reminiscent of the form of a whole square of the kind of a minus b, the whole squared, where we identify a with k and b with lambda. And the key, of course, is that a whole square, we know from our very early exposure to algebra, can be expanded in the form a squared minus 2ab plus b squared. Of course, this is an elementary form of the binomial theorem. Now, let's go ahead and expand the square via this. And if we did this, we get the expression on the right. Of course, the expressions become a bit bigger. We have, in fact, expanded out the square. But this is going to lead to simplifications. The key here is to observe that addition is an associative operation. We can add numbers in any order whatsoever. And so, inevitably, we take the expression on the right and group similar terms together and form sums. So, we group the terms involving k squared together, form a sum. Group the terms involving k together, form another sum. We can pull 2 lambda out of the sum because it's a constant. And finally, take the last term, lambda squared times p of k, form a sum involving those terms. Again, lambda squared comes out of the summation because it is a constant. Now we've got a yet longer expression on the right-hand side, but we are making progress because in each of the summands, we recognize quantities for which we have discovered identities. Let's start with the first one, the sum over k of k squared times p of k. We've discovered an identity for k squared times p of k. Let's promptly put it to good use, write it down. This is going to involve expressions of the form lambda squared times p of k minus 2 plus lambda times p of k minus 1 and sum over all possibilities. But the moment we do that, if you sum over all possibilities for k of the form p of k minus 2, what we in effect do is sum over all Poisson probabilities, p of 0, p of 1, p of 2, p of 3, and so forth, and of course that sum must be in fact 1 by normalization. Likewise, a sum over all k of p of k minus 1 again sums over all Poisson probabilities, and by normalization that sum is also 1, and therefore the entire expression on the right devolves and becomes very simple. It's just lambda squared plus lambda. Now let's look at the second term, a summation over k of k times p of k. Now this is very familiar. We've done exactly this in the computation of the expectation. But let's run through the calculation again. Replace k times p of k by lambda of p of k minus 1, pull out lambda from the sum. Observe we're summing over all the Poisson probabilities, that must be 1, and therefore everything becomes just lambda. And finally, the last term is the simplest of all, because the sum over k of p of k just sums over all Poisson probabilities. It is manifestly 1 by normalization, and we're done. Pooling our expressions together, we get the following result for the variance. The first summation involving k squared p of k gives us the term lambda squared plus lambda. The second summation involving k times p of k gives us a term minus twice lambda times lambda. And the third term involving a summation of p of k by itself gives us a term involving lambda squared times 1. And an examination of the expression on the right shows that lambda squared fortuitously cancels. You get lambda squared minus 2 lambda squared plus lambda squared, and it goes away. And so all that remains is a beautiful, elegant, simple expression, lambda. Let's quickly summarize. If x is a Poisson chance variable, then its variance is exactly the Poisson parameter, lambda. At this point, we've discovered all the basic features of the Poisson distribution. Our next three segments constitute dangerous bend digressions, dangerous bend topics, which show how the Poisson distribution arises naturally in the context of traffic, congestion modeling, queues. These considerations lead naturally to the Poisson process, which is a fundament in these disciplines. These topics are within our reach, within our grasp at this time, but they do constitute a slight digression from the main theme, and they are technically more involved, hence the dangerous bend designation. Sample them as time and inclination allow. If you wish to jump ahead, then this would be a good place to go right to the conclusion, to the summary, before we move on to the next tableau.